Let's start.
Okay, cool. Yeah, so welcome back for the afternoon session. And Siddharth Barman at IISc is going to continue his talk on welfare maximization in the context of right division. Yeah, please go ahead, Siddharth.
Excellent. Yeah, thanks everyone for participating on a Saturday afternoon. I'll continue talking about collective welfare and like just to spend a few slides recollecting what the background we did last time. So this is sort of the overarching theme of our pursuits. Like we are looking at these class of objective functions, class of welfare functions called generalized means. They have this general expression like this. So for different values of p, I get different instantiations of this welfare function. And so they are not only like a natural and algorithmically interesting class of functions, they come with a axiomatic uh, backing. So they're fairness axioms, starting with which you can show that these are the class of welfare functions, objective functions that satisfy those fairness axioms. So in the context of dividing goods, dividing resources in a fair manner, these are a natural class. They're not just natural, they're a axiomatically important class of functions to study. And this is what we'll do. We will look at different contexts, different settings, and try to maximize these P welfare functions. And three important members of this family are the utilitarian welfare, the social welfare, which is obtained by setting P equal to 1. So when P equals 1, this reduces to the arithmetic mean. And P tends to 0, again, this is a simple exercise that this expression reduces to the geometric mean, and this is called the Nash social welfare. When P tends to minus infinity, I get a purely fairness criterion called the egalitarian welfare or the Rawlsian welfare. So this expression is interesting for us when P is less than or equal to 1. And again, just to recall that Nash social welfare actually achieves a balance between the extremes of fairness and allocative or assignment efficiency. So this is an important member in this class, in the especially in the context of fair division, or when welfare with fairness guarantees is important. So throughout the subscripts, it denote the value that the agents will accrue through various divisions, various partitions, and so on. So that's the overarching objective function. We also saw a list of applications. I'll not go through them again. There's this popular website, splitit.org. You can go and check it out as well. What these applications kind of led us to was this very simple taxonomy over the settings you would like to consider. So and the taxonomy was simply based on looking at the goods that we are dividing among the n agents, the sort of the resource that we are dividing, and the good could be divisible or indivisible. So divisible would include things like food, land, water. Indivisible, the examples we saw were courses and housing units. Divisible, it could be heterogeneous, like land, of course, different areas, the same, say, square footage of land or same stretch of land has much higher value in certain areas compared to others. And this is referred to as cake division, the heterogeneous cake. And we kind of saw this result on maximizing Nash social welfare in this heterogeneous divisible goods case. So we did cake division last time, and today we'll do food division. And so this is what you get when you give me a post-lunch slot. These are the kind of things I'll start dividing. So food division will fall under this umbrella of homogeneous divisible good. Like if you have 10 kgs of grain and you get 1/3 of that, your value is 1/3 of the total 10 kg batch. So that falls under this leaf here, homogeneous divisible good. And at the end, I'll mention results about indivisible goods case. This is unlike this part of the subtree, which is sort of has a continuous optimization flavor to it. This is completely combinatorial. It's a partitioning problem here versus a fractional assignment problem on the left-hand side. Some sense this discrete indivisible case is the most active area of research in the past, let's say 4 or 5 years, dozens and dozens of work, lots of nice techniques, heavy hammers like real stable polynomials, and using, for example, Fisher markets in the service of algorithm design. So yeah, lots of interesting connections, lots of, in fact, open problems in this space. So at the end, I'll point to you to two surveys that talk about um, discrete fair division, so fair division of indivisible goods. And these two surveys have come out in fact, less than a month ago. So these are like fresh off the press surveys with many interesting open problems. So yeah, if you're interested, this is a great area to sort of explore. Right. So that this was last time, Nash welfare for cake division. Today I'll talk about homogeneous goods, and then the third part of the talk would cover indivisible goods. So yeah, let me move on to homogeneous. And the problem I'll study would be an online problem. I'll set up the model and describe it in bit detail. But roughly speaking, what's going to happen is that I'll will sort of receive these goods that are divisible, and so I can fractionally assign them among the agents. Um, the value of the agent would depend on the fraction that she receives. The challenging aspect would be that this needs to be done online. I'll give you a very nice motivating application to sort of that sets up this model or sort of substantiate the relevance of this online setting. And this is joint work with Arindam Khan, who spoke earlier in the workshop, and our very prolific intern Arnab. So this very recent work, kind of quite excited about this. So homogeneous divisible goods in an online setting. So here's sort of the mathematical or the formal setting. I will have agents again, 1 through n as before. And for each agent I and each good G, what we'll have to do, the decision that needs to be made, is to figure out a fractional assignment, right? So unlike the cake where there was just one cake and I was giving subintervals, now I have many goods, say M goods. And for each good G, and for each agent, I have to decide what fraction of this good G goes to this agent I. So this is the decision variable XGI. It's a number between 0 and 1. So that's the fraction of the good G that goes to agent I. And when it's summed across all the agents, so fix a good G, sum it across XIGs across I, that should be 1. So you have to take the good and like divide it fractionally among the agents. And the valuation is just simply additive. That is, each agent I has a number, has a value for this good G, that is this VIG right here. The total value that agent acquires by getting different fractions of different goods is just this sum. Right. So here VGI is a given number, it's a fixed number. That's the value that an agent I has for a good. These are the decision variables, XGIs. What is the total value that the agent gets at the end once you have made these fractional assignments across all goods? It's just the sum. So it's additive valuation, divisible, homogeneous good. Okay. And fine, like if it was an offline problem, that is, if I told you all these VGIs for all the agents and all the goods, these VGIs upfront, you can go and just write a concave optimization problem. In particular, these are the number of agents times the number of goods, decision variables. Look at this expression, maximize it. It's a continuous optimization problem. The objective is concave. Fine, you can find the optimal. So nothing sort of grand about it. What I'll do now is move on to an online setting where the problem really becomes interesting. And I am going to assume a normalization, and without which non-trivial results cannot be obtained, at least in the case of an adaptive adversary or a powerful adversary. And that normalization, I'm going to assume that for every agent I, so fix any agent I, if I look at the value for the grand bundle, so the value for all the goods, so summing over all the goods G, this total value is normalized to 1. So 1 is just a scaling thing. It doesn't have to be 1, but these values just sum up to 1. And we are in the goods case. So these are non-zero, non-negative, but yeah, this is the scaling assumption. I'm going to assume it's not going to be very apparent why I need it. I'll tell you one place where it is required, but yeah, like what I'm not going to spell out is like, if you don't have this, then you can't do much. Like pretty much in the online case, you're kind of going to get only very trivial guarantees. Okay. So as I said, this is a fairly well-motivated problem. And let me recall one of the applications that I mentioned um, earlier. This is work by Alexandra et al. This was done with Food Bank Australia. This is sort of a nice study where what they do is they like sort of look at the problem of so you have a hub, it gets food donations every day, and you have to distribute this food across different soup kitchens, across different, say, canteens. And you want to do it fairly. So the resource that's being divided are the food donations for every single day. So G here is going to be the food batch for every day. So every day you have and when the food arrives, it's only then, and it's only on that day that you know what the values are. So different soup kitchens sort of report their value, which you can think of it as like, this is the demand they have on that day. So food is a divisible resource. This is indeed an online problem. You cannot just store the food for, let's say, a month and then say, oh, you know what, just stay hungry for a month. At the end, I'll solve a nice concave optimization problem and give you a very optimal solution. That's not a luxury we have. This food allocation problem is also studied by other groups, in particular group at Cornell, Banerjee et al. Also look at this. They solve, in fact, this specific optimization problem for the Nash social welfare. So they have an intricate primal dual schema for exactly this optimization problem in this online setting. And they obtain competitive ratio guarantees, which I'll sort of compare with ours later. They're slightly better, but I mean, the punchline is that ours will work for all mean welfare, whereas they focus on Nash social welfare. Also, like, yeah, just to be fair, their results are slightly more robust. They work in this paradigm called algorithm design with predictions. So extending our work to that is also an interesting thread. But yeah, long and short, food bank problem is going to motivate this online study. And let me just spend one more minute and like spell out the connection. So what are the agents here in this fair division exercise? These are the soup kitchens, the canteens. So n, small n, the number of agents in this picture, for example, is 3. I have to divide food among these 3 soup kitchens. And what are the goods? And these are the food donations you receive every day. So at the hub, at the central hub, food comes in. This is the good, the first good. And the decision you make are these XIJs. So this is the XIJs for the first good across. So you point like 20% of the good goes to the first canteen, 30% to the second, and 50% to the third. Say on the first day, a lot of people showed up on the third canteen, you would want to distribute it like this. The point is that when the good shows up, the canteens, i.e. the agents report their value, you then decide these XIJs, and these are irrevocable decisions. Like once you have given them, the food is consumed, you're done, and you can't wait. So these have to be done online. You have to make these decisions as and when the day progresses. So this is on day 2, things starts afresh, another batch, another set of values reported by the agents, the canteens. You make another decision for these XGIs now for the second good, so on and so forth. And when at the end, like let's say at the end of the month or whatever stipulated window, you look at this value acquired by all the agents, and your overarching goal is to sort of find these numbers, XIJs, such that this function is maximized for whatever P you want. And we've discussed this at length, that this is a good welfare metric to study. For example, Nash is a good welfare metric to study in this context. It's a good, fair way of, axiomatically justified, fair way of making decisions. So that's not just a natural objective, but a well-founded one in this fair division exercise. Okay, that's the setup. I will now kind of jump to the algorithm. So just make a mental note of what we are doing. And very surprisingly, and sort of the algorithm is going to be hauntingly similar. I will again, it's few lines of pseudocode. I'll be able to express the main ideas. There are finer details, and I will not subject you to them. I invite you to read the paper for those nuance points, and there's certain details that I'll gloss over. My purpose is not to sort of like subject you to every possible detail in all possible cases. I want you to convey, I want to convey the main idea, the guiding intuition that works here, and the sort of how clean this like algorithm template is. So the sort of elegance of it is what I'd rather focus on. I will present the technical ideas, but just roll with the punches. I'll not there'll be points where I'll skip low order terms and so on. So just, yeah. It's more the intuition and the sort of proof sketch than the exact details. So yeah, here's the algorithm. In fact, it's a 3-line algorithm. What's impressive about it is that this algorithm will work for all values of P. It's a family of algorithm. It's governed by this threshold T. So for different P values, for different P means, I will only change this threshold T, and I'll get the algorithm for that P value, for that generalized mean. And we'll show that for a wide range of P, this single template, this single algorithm design will work to give us essentially tight competitive ratios. So recall from Professor Amit Kumar's talk that in the context of online algorithms, the metric of choice is competitive ratio, which in this case is the optimal like P mean welfare when computed, say, offline or at the end of the entire exercise, divided by the P mean welfare. So the optimal by the P mean welfare achieved by the algorithm. So the closer to 1 that ratio is, the better it is. You want that ratio to be small. The competitive ratio, so the analog of approximation ratio in the online world. So here's the algorithm. It works with a threshold tau. And what it does is it maintains 2 subsets of agents, right? The first is an active set of agents, which are agents who have yet to acquire a value of tau. So let me be specific. As the algorithm progresses, it makes allocation decisions. The next good comes, it fractionally assigns it among the agents. The subsequent good comes, it again fractionally assigns it among the agents, so on and so forth. So as these fractional assignments are happening, the values acquired by the agents keep on increasing, so that the sum of xig, vigs keeps on going, summed over all the goods that have been assigned so far. So what you do is you look at this threshold tau and maintain those agents that have yet to acquire a value of tau, right? So initially, all agents are active because they've only acquired, say, value 0, and say if tau is positive, in that case, all agents will start out to be active. As the value increases for agents that cross this threshold, they have already acquired a value of tau, you sort of kick them out of the active set. You tell them, look, you know what, you have received enough, just be happy, go out. The second set you maintain is a set of vulnerable agents, which is actually a subset of A. So V by definition is a subset of A. And these are agents for whom, if you look at the total value of the goods that is left, that happens to be small. I will quantify what I mean by limited value left, but here is where I use the fact that the grand bundle is of value 1. So I look at every agent that is active, so still hasn't received a value of tau, and then I look at the total value that has gone by. So not just the value that this particular agent has acquired, but the total value of the goods, the cumulative value of the goods that have gone by. Subtract 1, like this quantity from 1. So that's the value that still remains, right? So I'm saying, okay, here's an active agent. In the future, if I were to give her all the goods that remain, even then that's a small number. So that agent is going to be vulnerable, right? Like it's now in a red flag zone that even if I assign this agent everything that remains, like her value is small. So those are defined to be the set of vulnerable agents. Okay, and that is it. Like once I have that and these two sets I can maintain online. The only thing I need is this total value normalization. Once I have that, I can maintain these sets based on what I have seen so far. And here's this online decision, this online irrevocable decision. The good comes in. It's a fractional, like it's a good that's divisible. I take 1/3 of the good and then I uniformly distribute it among all the agents. So this is more of a fail-safe. In the analysis, it won't play like at least in the presentation, it won't make a sort of important dent. This is important. Like when you read the paper, you'll realize that this is a good thing to do as a backup, right? So at least you ensure that every agent gets some bare minimum value. So this is what you do. Let's say you get this 30 kgs of rice, 1/3 of it is 10 kgs. You just divide that 10 kgs uniformly among all the n agents. Fine. So that's gone. Then you look at another 1/3 of the good. So you pick the agent that has the maximum value for it among the active ones. So this A here is important. So you look at agents who are active. Among them, you ask them, okay, what are your values for the good? The one that values it the most, you give it to her. So that's a purely greedy step. A large chunk of the good, 1/3 of it goes to this active agent who has the most value. Another 1/3 thing, you do sort of an egalitarian exercise. So interestingly, at a high level, this is a mix of the two extremes. 1/3 or like some part of it, you're purely being egalitarian, uniformly distributing. The other 1/3, you're just doing a very greedy exercise, giving it to the agent that values it the most. So the 1/3 that remains, you assign it among the vulnerable agents. So that's the algorithm. Yeah. I'm still surprised that this simple, like very clean, direct idea works for such a general class of valuations. Yeah. Analyzing it is a fun exercise, but at least in terms of the design aspect, it's a rather clean thing. Let me just make a quick note that if my goal was only social welfare, only like the arithmetic mean, then all I had to do was this step and not even look at greedy, not even look at active set. I could just look at all the agents and every time just greedily give it to the agent that values it the most. So that would maximize social welfare. This is a mix of the whole thing. Okay. All right. So far so good. Any questions? No, I believe. Right.
Yeah, nothing so far.
So here's before I analyze it for like one case, one particular value of P, here's the set of results we obtain. And this is by no means a single analysis. Every colored interval you see here is a different case. But what we obtain is that as you as you pick tau, the threshold of the algorithm for different values of P, these are the competitive ratios you obtain. Let me parse through this picture. It's sort of the summary of all results, if you will. So if I start at so this x-axis is this exponent parameter P for the P mean welfare. If I start at -infinity or a very small, this is egalitarian welfare. For this, what we can show is that for a specific value of tau, the competitive ratio is something like O tilde of square root n. So up to log factors which are being hidden, subsumed in this O tilde notation, competitive ratio is square root n. And one can show that this, in fact, up to log factors, this is tight. No online algorithm can achieve better than square root n, like omega square root n competitive ratio. So this is a tight guarantee. This ends up being tight till, in fact, something like the harmonic mean. So till -1, you have a lower bound and an essentially matching upper bound through this algorithm. Tau, in fact, in this entire range stays the same. So all these phenomena that emerge were not obvious to us a priori. And like, this is quite interesting that, yeah, like you have these competitive ratio, there's this like a sudden threshold phenomena and it drops like the competitive rate. If you look at it, this x-axis is not to scale. This from -1 to -infinity, you have a relatively high competitive ratio, albeit it's tight. But suddenly from harmonic mean to this term -1 over log n, the competitive ratio drops. And again, you can show that maybe not up to polylog factors, but there are morally matching lower bounds even in this regime. And these are slightly complicated expressions. To analyze the competitive ratio of the algorithm in this range, you have to use like series expansion ideas, tricks from calculus, so on and so forth. So you do get competitive ratios that look, for example, in this range. Again, -1/4 isn't nothing sacrosanct about it, but yeah, for some constant that's say smaller than -1/2 or -1/3, you get a drop like n to the 2, the absolute value of p. So once you get to something like -1 over log n, the p value, you have now dropped. If you plug this in, you have now dropped to a polylog factor, and then it stays that way. So in particular, for Nash social welfare, there is a tau value that I can plug in. There's a threshold that the algorithm can be operated with, and I get a competitive ratio of log cube n. So Banerjee et al. Actually just study this case and show that the upper and lower bound in this case is log n. So we are again log square n off. Yeah, the point, however, is that their algorithm is tailor-made for Nash social welfare, uses like a fairly nice primal dual schema. You do like this algorithms with prediction ideas kind of come in there. But so sort of again, the fact is that it stays this way. And there are discontinuities here. This I think is more because of our analytic limitations rather than a natural limitation of the algorithm. So that's something to sort of look forward to in future work. But yeah, it's kind of stays to log cube n. And as I mentioned earlier, for p equal to 1, it drops to 1. You can do the optimal thing even in an online setting. But yeah, it stays log n up to pretty much up to 1. Now that's the sort of entire spectrum of results we obtain through the algorithm. Let me repeat, it's not that there's a singular analysis that ends up working. One has to sort of work through it and like really sweat out the case analysis and do these different regimes properly. However, yeah, the nice thing, the one that I like about this result, it's kind of sort of find it interesting, is that yeah, a single algorithm, single idea kind of works through for this entire space of valuation function. So that's this. Yes.
May I ask a question?
Sure.
So to interpret this fact that there's this sharp, you mentioned that when the slope comes down, there are somewhat matching lower bounds, right?
Yes, yes.
So is it fair to say that the value of tau somewhere between this -1/4 and this -1 by log 2n, there is a phase transition?
Yeah, I think so. Yeah, it seems like it. So again, yeah, this is not tau. This is the p value. The
p value, right? So with respect to p value, sorry. So with respect to p value, there's a phase transition. I say this because it's not an art sort of a limitation of your algorithm. Because if you have a matching lower bound, then it means that in the online setting, this is the best one can hope to do, right? Isn't that the way the is that the way to interpret the lower bound and your matching upper bound?
Yes, and let me be a bit precise about it. So the lower bound actually looks like square root n up to log factors till say -1. In fact, you can push it a bit more. So it is quite high. So in this, again, neither the x-axis nor the y-axis or scale, this is more an illustration. This is a large number compared to log n. And suddenly, when p goes from here to, let's say, below, the lower bound also drops to log n. So close to 0. So say in this regime, you have a lower bound of log n. Here, the lower bound is quite high. So there is a drop, and this is not a large range. Like this is like minus infinity. So a lot of heavy lifting is being done by this small looking interval. There is a phase transition here, right?
Yeah, because of the comparative length of this portion with that, it just seems like there's a drastic drop. So thank you.
Yes.
Another question in the chat. Should I read out?
Yes.
Yeah.
My analysis is tight. So Shivika is asking, is your analysis tight for egalitarian? Tight again up to log factor. And let me take credit. Okay, I have a visitor among. Up to log factor, yes. For egalitarian, the analysis is tied to the extent, like not just the analysis. It's there's a lower bound of square root n. We get an upper bound of something like square root n log n or log square n. So it's the log factor being hidden, but up to that it's. Yeah, and prior to this work, there was no known algorithm even for the egalitarian welfare, let alone for others. So the only known result for this whole x-axis was naively the social welfare and this Nash social welfare. So this egalitarian welfare, even as an algorithmic result in and of itself, is a nice contribution. In fact, that's the proof sketch I'll give you will be for egalitarian. Okay, can I move on? Okay.
Yeah, please. Sorry.
Fine. So here's the quick repetition. That's my algorithm. I have a single set of active agents. The algorithm performs with a given threshold tau. The set of vulnerable agents for whom the total value of all the remaining goods is small. And for each good, I just make 3 decisions: uniform over everyone, greedy in the active set, and uniform over the vulnerable set. That's it. Okay. As I said, like the analysis for different values of P is involved. Nash is slightly simpler, so you can sort of easier to read. But let me give you the key idea, one key idea, and exemplify it by looking at the egalitarian welfare case. So by which I mean, I want to divide the fractional goods such that the minimum value across the agents is as high as possible. So the P equal to minus infinity case, I want all agents to have a high value at the end of the fair division exercise, at the end of it, once I've allocated all the goods. Again, to simplify exposition, I'm assuming that I know this optimal upfront, like I know eta star, the optimal egalitarian welfare. Certainly, I don't know the solution. I don't know how each good is divided. All I'm saying is that there is a solution. There is a way to fractionally divide the goods such that every agent gets eta star. How do I deal with this sort of in the paper, or like, because this is an assumption? Well, what you can do is like run this algorithm for d-adic scales, like 1 over n, 2 over n, and then from 2 over n to 4 over n and so on. So that's a place where you lose a log n factor. So you just sort of guess where the optimal is and run those copies of the algorithm in parallel. The goods are fractional, so you can do all this. Again, read the paper, talk to me offline. For the time being, let's just roll with me and like imagine that I know this eta star. That is, I know that there is a solution wherein all agents are getting a total value of at least eta star. Fine. For this case, what is the threshold? This is what I do. I set the threshold to be eta star by square root n, the number of agents. When I set the threshold to be that, my definition of the active sets is that these are agents who have received value less than eta star by square root n. So that's my threshold. I'll only keep an agent active till her value hits this threshold. And in this case, the vulnerable set are the agents for whom the total value left is eta star by 2. So that's a really small fraction. In particular, it says that, look, like if you have become vulnerable, and if I give you all the remaining goods, even then you're only going to get eta star by 2. So that's the definition of a vulnerable set. This online decision stays the same. Okay. So that's the algorithm for egalitarian welfare. These are the instantiations. this changes for different p-values. For Nash, this is a more generous threshold and so on. So yeah, we encourage you to read the paper, but once you've seen the presentation, a lot of things would be sort of clearer, like why are certain decisions being made. Okay, as promised yesterday, I will give you proofs that fit in a slide. So yeah, conforming to that, here's the sort of proof sketch of why this works for the case of egalitarian welfare. So the first observation I'm going to make is that if I look at the social welfare acquired by the algorithm, that's actually upper bounded by this expression. Why is that? So let's just ignore the uniform part. That's more a fail-safe. So let's look at the social welfare that's assigned to agents as they are part of the active set. So once you're off the active set, you're not going to participate in this argmax, you're out, and you'll not get any fraction of the good, at least like these two parts, because V is also a subset of A. So what you are getting value, you are acquiring, any agent is acquiring value till she is in the active set, and which means that any agent, the upper bound on that is by this threshold is eta star by square root n. There are n agents, so the total social welfare is at most eta star by square root n. Note that this is an upper bound. I'm saying ignore the uniform part for the ease of exposition or for this presentation. So just look at these two parts, and the total value that's acquired is only when you are active, and this is what it is. Fine, that's an upper bound. Here's a next useful observation. So look at an agent, and she is now a part of the vulnerable set, right? So note that if no agent ever becomes vulnerable, you're actually golden. You have ensured that if all the agents stop being active, it means that you have assigned eta star by square root n to everyone, which means that even the algorithm has hit this egalitarian welfare up to a square root n factor in the denominator. So you wanted to give everyone eta star, you have given everyone eta star by square root n, fine. Your competitive ratio is square root n, done. So the only bad case is when you have vulnerable agents. So let's look at one of those. So fix an agent I, she's vulnerable. Now, how has this happened? This has happened only because I has lost, and I'll explain what this means, at least eta star by 2 of her value. So this is slightly a delicate observation, so let me spell it out. What I'm saying is that, look, at the point that I became vulnerable, there were goods that were assigned to her in the past, the irrevocable decisions you have made. So say there's some good G, the optimal was giving some delta fraction of the good to this agent, but you did not, the algorithm did not. So, but when the algorithm did not, so, but this, like at this point, eta star over 2 value is left for the agent. So that's why I is vulnerable. So it has to be the case that the agent has lost at least eta star by 2 of its optimal value. So if you like, as an analysis, if you compare the wrong decisions that you have made, by this time you have already, like goods that should have been assigned to I are fractionally assigned to someone else, and that value is gone, right? So this is just because even if I now give you everything, you'll only get eta star by 2. Okay, but this is, note that every time I take delta, which is supposed to be given to I in the optimal, and give it to some other agent, I'm actually doing a greedy thing. That delta fraction that I'm taking from a vulnerable agent I and giving to, say, some agent A, that agent A has higher value for the good than I. So in terms of social welfare, I'm doing better. Let me say this again. Pick a good G, and let's say this delta fraction of the good in the optimal was given to I, but you gave that fraction to some other agent A. Your decision must have been that agent would have been the one that has the maximum value for it. That's the greedy decision. The factor 1/3, I'm ignoring that, so just to squint your eye a bit. But what I'm saying is this delta fraction, instead of going to I, has gone to some other agent. That agent must have had higher value for the good. It's only then that you have done this pass, done this transfer. So So what it means is that the social welfare of the algorithm is actually at least as much as the social welfare you have lost among all vulnerable agents. So if for every vulnerable agent, this much social welfare is lost, you have reassigned it, but you have reassigned it greedily. So you've done a better job, at least in term, you have assigned it to higher value agents. So you have this inequality. Social welfare acquired is at least as much as social welfare lost. What this means, and if you eta star cancels out, is that the vulnerable set at no point of time is of cardinality more than 2n. You're always maintaining this invariant that not too many agents fall in this regime of being vulnerable. And that is it. The point is that I am still assigning uniformly among V. So as soon as an agent I becomes vulnerable, from the point that from that point onwards, she's only competing with other vulnerable agents for at least 1/3, for this 1/3 of the good that I'm uniformly distributing. So that 1/3 actually, so you have eta star by 2 value total left. This again, there should be a 2 here, because it's eta star by the cardinality of moving cardinality of V. But what this ensures is that, right, you have of this, what is left, eta star by 2, you are getting a 1 over cardinality of V fraction, which is again eta star by square root. So yeah, it's a rough sketch, but I hope like the idea is clear. What I am doing in this case is using the social welfare calculation to bound that there will never be a lot of agents in the vulnerable set. And hence, so say vulnerable set was always small. In fact, that's exactly what we are showing. A uniform distribution over it kind of guarantees, even if you land up in the vulnerable set, you will get a sufficiently high value. All this means is that every agent I'll guarantee gets at least eta star by square root n, and that's the competitive ratio I told you. The log n terms I'm hiding and so on and so forth. But yeah, I hope the sketch is clear. So here, yeah.
Just a thought experiment. Why did we allocate anything at all to the greedy? Why did we do that? Just to get the bound that every the person who, why did we do that? Why not assign everything to the uniformly first and then to the vulnerable people?
Oh, you mean this step?
Yes.
Oh, it's this step that actually gives me this inequality.
So that's the part I'm trying to understand. So.
Let me try to like repeat and see if I can. Should have like made more, written more equations, but here's sort of what I'm trying to say. So imagine a good G, any fixed good, and let's say this good was completely assigned to a vulnerable agent. The optimal completely assigned it to I.
Yeah.
Fine. Then, however, what you are doing is just this greedy thing. You're completely assigning to this agent A. But the choice of A ensures that VA of G is more than VI of G. You are looking at, so the I is vulnerable, so she is active, which means that I picked agent A instead of I, means that the value that A had for that fixed good G was more than I's value.
Right, whomever opt gave to, that's the thing.
Exactly. Whomever this greedy gave to has higher value.
Then, yeah. Okay.
So you are misassigning this good, say entirely to A, but this misassignment will not hurt you on social welfare front.
Right. Vulnerable agents are subset of active agents. And so exactly. A really highly valuing vulnerable agent would also be considered during the greedy allocation. So if there's some there, that person would be a candidate to be assigned. So I'm not actually missing out on anything.
Exactly. So, yeah. Okay. So this by definition is always a subset of B.
Right. Okay.
Yeah, and if you think this was confusing, please go and read the paper. You'll have fun. But yeah, it does. In all seriousness, these are sort of nice ideas that kind of go in, and it's sort of a surprise still to me that like a single template like kind of works for, gives us this entire slew of results. So that's this reference. As I said, this is joint work with Arindam and Arnab. I'm slightly behind schedule. way behind schedule. So let me just quickly talk about indivisible goods. So this will be the last part. Slightly less technical. I'll try to give you more of a survey of this sort of results in this space. It's, as I said, this is actually one of the more active threads in this picture here. Maybe dozens and dozens of papers quite regularly in this space, and very nice and challenging algorithmic problems. So finally, I'm now going to talk about fairly dividing indivisible goods, so a discrete optimization problem. And as always, my objective will be p-mean welfare. So how does the problem look like in this combinatorial setup? Well, now what I have, as before, are n agents, but the decision I have to make, the algorithmic output, is a partition. So I have m goods. These are not divisible anymore. This is not a K. These are discrete indivisible goods. So the problem at hand is the following. I have to find a partition of these goods. So these pairwise disjoint subsets where A1, this subset of goods A1 is assigned to agent 1, subset of goods A2 is assigned to agent 2, and so on. So I have to make this allocation decision and just go over all such allocations to find one that maximizes this p-mean welfare. So what's important to note here is that now VIs are set functions. So for every agent A, the preference, the cardinal preference is specified by the set function VI. So for agent I, VI tells me what is the value that agent I has for different subsets of goods. So, and these set functions can be complex. In all its generality, these are entities that live, like that need, let's say 2 to the m amount of size table to even specify. So huge, complicated objects in complete generality, but of course it's too unwild, like it's too wild. We'll kind of look at the standard valuation classes and talk about results in that space. But this is the general form of the problem when I'm dealing with indivisible goods. I'm looking now at a partitioning problem, looking at a problem where the goal is like this combinatorial optimization exercise. Okay, and as I said, of course, the VIs are set functions. They, for every subset of goods, VI tells me the value, the numeric value that the agent I has for the subset. And the algorithmic results obviously are going to be based on different valuation classes. What are VIs? Based on that, the problem becomes easy, hard, tractable, very intractable, so on. So two special cases of this general boxed problem has been studied relatively much more than the general p-mean form. One is social welfare, that is the standard arithmetic mean. It's kind of an important problem in mechanism design, specifically in combinatorial auctions. So you can look at, for example, the textbook on algorithmic game theory by Nissan and others, in that the parts that deal with combinatorial auctions focus a lot on social welfare maximization. It's an important problem that has received a lot of nice algorithmic ideas, rich literature on it, even like before this p-means idea sort of came to the forefront. The other extreme has also been studied, which is referred to as the max-min allocation problem or the max-min fairness, which is egalitarian welfare. You want to find partitions that maximize the minimum value across agents. So the maximize min of VI, AI. Restricted cases, this is also referred to in algorithmic literature as the Santa Claus problem. So again, nice use of things like hypergraph matching, configuration LP. So good amount of literature in this space as well. But let's kind of move, I'll give you references. You can look up those special cases. For general p-mean, the problem is rather challenging, specifically if you go up to like encompassing valuation classes. So this is joint work with Umang, who's here chairing the session, Anand and Ranjini. What we show is that for this broad class of sub-additive valuations, I'll not really spell this out, what sub-additive means, but these are, think of them as the most general class for which you can hope for positive results, and complement-free valuations. For them, what we obtain is something like order n approximation. So subadditive is a broad class. It includes, as very special cases, submodular, additive, XOS valuation. So it's a rich class. For this, we show that you can get an order n approximation for P mean welfare for all P. Nice combinatorial algorithm. Similar result was obtained by, at least the approximation guarantee was obtained by Chaudhary et al. And if you think this is not a great approximation factor, well, here are my two defenses. First is that we actually show this is tight in a standard Oracle model. So in this setup, I can't really spell out the entire valuation. Like I can't give you, for this subset, this is the value, for this subset, this is the value. That's an exponentially big input. So algorithmic results deal with this by working with valuations that are specified through an oracle. So you have an oracle, you submit a subset, the oracle returns what is VI for that subset. So that's called the value oracle. And what we show is that in such value oracles, this order n is tight. You can't, that's it. Like this is the best you can hope for when you are dealing with subadditive, or in fact, a class below, which are called XOS functions. Yeah, so that's the other defense I have for this approximation guarantee, that in many cases, the number of goods can be large, but the number of agents participating in the fair division exercise is not astronomically large. So you are, say, dividing inheritance, and is the number of siblings, which can be manageable, but nonetheless, from a theoretical perspective, and if you are confined to value oracles, this is the best you can do. For now, the sort of point is right. It's hard for for general valuation class, hard as in its order n approximable and theta n approximable in the value oracle model. What can you do for special classes? So the joint work with Ranjini, we show that, okay, drastically things improve if you assume that the valuations are identical. So they are still subadditive. These VIs are a general valuation class, but it's the same for all agents. All agents have the same preference. Makes sense in certain settings. And here, if you use what is called a demand oracle, you can actually get a constant factor approximation. And what's kind of nice about this result, I have not mentioned it explicitly in the slides, that what you get is like a universal guarantee here. So here you can find a single allocation that achieves a constant factor guarantee for all P mean welfares simultaneously. So I'll give you one allocation and I'll tell you, you know what, go pick your P, and this single allocation that I've given you will be within a constant factor. Its P mean welfare will be within a constant factor of the optimal P mean welfare. So the optimal can change. You can change the P, but I'll just give you one fixed allocation. This is the case when all the valuations are identical. There's a very nice recent work by Babayev et al. That look at sort of binary submodular case. So these are matroid rank valuations. So these VIs are rank functions of matroids. In this case, again, you can get a constant factor approximation for all P mean welfare. So this is for the general P mean. I mean, the sort of one-line summary here is that, yeah, this is a challenging problem. Particular even for P, when P tends to minus infinity, the egalitarian welfare itself is challenging. So it's hard to get sweeping positive results. But what about Nash social welfare, right? Like so again, a very important element in this spectrum of welfare functions, the geometric mean, what can we do for that specifically? And this is a very sort of active and bubbling like thread of research, many papers, many groups working on this. It has a biased list. This B is me most, and but yeah, like lots of. I'll point you to surveys that actually cover the literature a bit well, and you can obtain, again, depending on the valuation class, like a range of results. So, for example, if the valuations are additive. So VIs are additive functions. So your value for a set is just the sum of values of the goods in that set. In that case, the best known approximation guarantee is E to the 1 over E. And for technical prowess, you can look at this, like results in this space. So there are prior works that use, for example, real stable polynomials to achieve approximation guarantees for additive, use novel convex relaxations like spending restricted ones to obtain constant factor guarantees in this space. So yeah, bunch of work here, and for slides like bit generalizations like budget additive and so on. So good set of results, like nice technical depth here. There's a very nice recent work by Wondrak and Lee, which achieves a constant factor guarantee for the case where these VIs are submodular. So it uses multilinear extensions, so on and so forth. And I mean, if you're looking for like complicated results, so there's a recent work with Pooja Shivaka, I think, who's also attending the talk, Anand, where we kind of use demand oracles and obtain like the break this order n barrier that I mentioned for subadditive, but for a class below, which is called XOS. I'll define this class in the next slide. Yeah, so again, complicated results are there. So Saturday, let me just pick one that's sort of easy to describe and like, I have 5 minutes, Umang.
Yeah, please go ahead. I think
Yeah, so I'll wrap up, and with this final result, it's sort of a joint work with Paritosh, where we obtain a constant factor guarantee for this class of valuations, which are called binary XOS. So I'm going to present an approximation algorithm or solve this Nash optimization problem for VIs that are binary XOS. So that's the final step. I'll give you some like literature and point you to certain surveys and then sort of stop there. Okay, so what are XOS functions? These are valuation functions. And in this case, these are set functions that are defined to be pointwise maximizers of additive functions. So in particular, I will focus on what I call binary XOS. So these are a special kind of XOS functions. And you can think of them as a function that's specified by a set family. So I'm not saying that this entire set family is given to you as input, or not even saying that this is a small, like a polynomially small set family. I'm just saying V is a set function. It's defined, say, over a universe of elements. And how is it defined? It's defined by considering this potentially large set family. So each F1, F2 are like subsets themselves. And for any set of elements S, for any set of goods S, the value that you have for this set is obtained as follows. So you go through this entire family, pick each set, look at the intersection, the size of the intersection, and then select the maximum one. So that's the definition of what it means to be binary XOS. If you sort of, instead of looking at the intersection, if you replace this by some additive function, you get the general XOS. I am, for the purposes of this specific result, looking at valuation functions that have this form. They do include interesting special cases. For example, if each of these FIs are independent sets of a matroid, then V becomes the rank function of the matroid. Right? So you're just looking at the largest intersection among all independent sets. That's a matroid rank function. This is more general. I'm saying I'm imposing no structure on these FIs. This is any set family, and you just obtain it this way. Let me repeat the fact that I'm not saying that I am going to give these FIs to you as explicit input. I'm just saying you have oracle access to V. Just so happens that this V always has this form. There's some implicit large family. The function values are coming out of that. So note that because I'm looking at cardinalities, these things are like for any S, the function value is the V value, the value of this set. It's going to be at most size of S. But yeah, these things also have like binary marginals, so on and so forth, and hence the word binary XOS. Useful class, in the paper, we spell out some like use cases and point out the fact that they can be used to say capture preferences in like spatial or temporal settings. So think of these FIs as contiguous slots on a machine. How many of them do you get? That's the function value. So that's a function class I'm going to look at. And in fact, yeah, let me again, like last time, go overboard by a few minutes, but it's a short result. So focusing on binary XOS, this is I'll give you another connection between NV freeness, a sort of a slightly grander form of NV freeness, and NAS social welfare. So sort of hammering in this like relation between these two notions a bit deeper. And for that, let me define two things, right? So I start with any allocation. So this is a partition of the n goods. Now for every agent, I define two sets. Let's say HA and GA. HA is a subset of agents. These are agents who are getting subsets of size 4 more than A herself. Okay, let me say that again. Pick any arbitrary allocation A1 through AN. Pick any agent A. Look at all other agents that are getting like 4 times as many goods as A. So in the binary XOS case, you can ensure that the value and the cardinality are aligned. So that's why this makes sense. I've replaced values by cardinality, but if you want, you can think of this as being values, and both are interchangeable in this specific context where I'm looking at this specific like this valuation class. So these are high agents with respect to A. They are getting 4 times as many goods as A herself. Okay. And GA be the grand bundle. It will be the bundle of all such agents, right? So I look at all agents who have really larger number of goods than you, and I club all their goods together. This is my set GA. Okay. So is the definition clear? Okay, so these are the two sets, and here's the lemma. I'm not going to prove it. It's a subtle counting argument. It's a careful counting argument. But what it says is that if you give me an allocation where I do not envy this grand bundle by more than a factor of 1/2, sorry, there's a typo. This should be A. What I'm saying is that for every agent A, the value that she acquires from the subset that's been assigned to her is at least as much as half of this grand bundle GA, then the number of agents that are alpha suboptimal is at most n by A. So slightly, as I said, it's a careful counting argument. I'll not give you the proof, but this is an NV to Nash kind of a statement. I'll show how Nash comes in. But what interestingly I'm arguing is that, yeah, like you are not envying this entire set. And one can show that standard relaxations of envy freeness does not work. This strengthening does. So I don't have envy not just against these agents individually, but against their entire collection of goods. The second part is important. Let me just explain that, and that will clarify the whole lemma. When I say alpha suboptimal agents, I mean agents who are getting value less than 1/alpha times their optimal thing. So the second part, the implication of the lemma is that I look at all agents for whom the value in the allocation is 1/alpha less than the value in an optimal allocation. The number of such agents S is at most n/alpha. And this holds for all alpha. So I'm saying, okay, how many agents are 4 suboptimal? They are getting 1/4 times the optimal. What the lemma says is, oh, if the allocation has this property, then the number of such 4 suboptimal is n/4. And I ask you, okay, how many agents are 16 suboptimal? Well, you can say, okay, how many agents are getting less than 1/16 times their optimal value? You can tell me that, oh, it drops linearly, it's n/16. How many are getting log n? Then that will be n/log n. So for any alpha, this holds true. So great. And that is it. I'm slightly over time, just bear with me. This is sort of the last technical slide. Once I have this lemma, I'm not going to prove it. It holds for binary XOS. But this, I mean, does give me a constant factor guarantee for NAS social welfare. Why? Let's just look at the ratio of the NAS social welfare. So the numerator is the one that's achieved by this allocation that has this sort of a grand NV guarantee. The denominator is the optimal NAS social welfare. It's the NAS social welfare of an optimal allocation. So I can just write it as a product of these ratios. The 1/n exponential, like the exponent stays out. Now what I do is partition them among, like I look at d-adic values of alpha, so powers of 2. For each such thing, the ratio is like 1 over alpha, or within like 1 over alpha and 1 over 2 alpha. So this 2 to the k, think of this as the alpha. The number of such agents will be n over 2 to the k. So when you multiply this 1 over n, you essentially get 1 over 2 to the k. So all I'm doing is applying this result for alphas that are powers of 2. So for alpha equals 2, 4, 8, so on and so forth till infinity. And this is the expression I get. If you work this out, this is a nice exercise and series at this sort of a product of 1 over 2 to the k to the power 1 over 2 to the k is close to 1 over 16. So that gives me the approximation guarantee. Fine, like even if the technical details weren't clear, what I'm saying is that this is a nice property to have. Like if you have such an implication, this proof actually does not require anything about binary XOS. What I need the binary XOS is to show that such grand NV freeness implies this sort of linearly decaying suboptimality, but yeah, it's a good takeaway to remember. Like if you can establish such an implication for other valuation classes, you will again get a constant factor approximation guarantee. So you just ensure that like the number of alpha suboptimal like drops as a factor of alpha, a good property to have. Okay, that's the theorem, which means that if I have such grand NV freeness, I do have constant factor approximation guarantee for Nash social welfare. There's a simple potential way of achieving such an allocation. You should keep doing local updates. You can find such an allocation. I'll again, in the interest of time, spare you the details. These are the two papers I talked about, the online result and this binary XOS case. Yeah, many interesting problems. I'll in fact point you to the survey next slides that have many more nice questions in this space. But yeah, the one that I like is this one that I told you that for identical valuations, you can get a constant factor approximation guarantee for even subadditive ones, subadditive valuations in the demand oracle case. Can you extend that, right? So can you look at fair division instances where there's a fixed number of distinct valuations? So the number of agents can be large, they can be n, but I'm saying that let's say there are only 4 different valuations. So each agent has one among these 4 different valuations. For those sort of instances, can you obtain nice approximation guarantee? So that's I'm referring to that as bounded heterogeneity. So that to me would be an interesting results. Yeah, query communication results, now social welfare for in this more general Oracle models. Here are the surveys that I've been promising you for quite some time. Like as I said, less than a month old actually. Both are on archive with great open questions dealing with different forms of NV freeness, and so going beyond just p-mean welfare and so on. There's a nice survey by Varut also that talks about constraints. I've looked at the unconstrained problem pretty much. Yeah, so this is also a good read to understand the landscape of results. These are the textbooks I mentioned last time, way over time. So just quickly stop here and thank you for your attention. Yeah.
Great, thanks a lot, Siddharth. Maybe a quick question.
Yes, yeah.
So I'll just ask one. So you mentioned the Banerjee et al. Result, right? So there also, do they assume that the sum of this normalization? I guess they do, right? You said because without that you can't get any guarantees.
Yeah, they do. They assume something. They work with something which is called algorithms prediction. Mm-hmm. So they assume that I have a estimate of this total.
Oh, I see.
And okay, as your estimate degrades, your quality degrades. But if it's exact, then that robustness is something that is nice to achieve for, say, like egalitarian and so on. So that's a good, this is an active like subfield, right? Online learning with, or online algorithms with, online decision making with predictions. So that's the flavor of their results. Yeah.
Okay, so I guess let's have maybe a 2-minute break before the next talk. And thanks a lot, Siddharth. Fantastic talks both of them.
Thank you.